here to cover one topic on image classification techniques. I hope you can see my PPT and you're able to get my voice, plus the video also. So basically in this 4.5-month certificate program, which is an online program on remote sensing, GIS, GPS, digital image processing and their applications. The first module is going on, and in this module you have already covered on remote sensing topics, and then a lot of topics on image processing is also covered. So today I'm covering as a new topic in the series on image classification techniques. And in this I will have two lectures. Today first is on image classification, and on Friday, that is second lecture, will be on accuracy assessment of the classification what we are learning. So topics, if you see in this today's lecture, you will see I'm going to cover on separability analysis, image classification, and on Friday I will cover accuracy assessment, that is the classified output to be checked how much it is accurate. Before we go further these topics, we should learn and understand what is image in a context of when we are doing digital image processing, not just a book definition. So by book definition, this talks about it is a pictorial representation. So pictorial representation is defined as image what we get through camera. It can be your personal mobile camera or satellite or aerial photographs or any other camera. That may be a book definition, but when we are going for digital image processing, maybe that definition does not give us much understanding what is image. So here I'm just listing few images like this one, and you can say you can define this rose image. But when I start asking how you define this is an image, then you may get lost. And same way, this you can say it is an image, but again question is same, how you define this image. Second, this one and this one. So these are very common personal photography we are doing nowadays with the mobile camera. And the question is same, how you define these images, so that if you want to do processing on this image, any manipulation, so you should understand what this image is and how to process this image. Parallelly, we can see the example of some satellite image. So this can be a panoramic image, and where you are seeing this to be a water, and this can be a land area. Now, if you take this small portion of this image and zoom it here, what you get basically, you just get black and white or gray type of pixels. So these squares are called pixels. And further, if you zoom it, basically you found these squares are represented by numbers, can be a float values or integer values. Here I'm showing these values are integer values, and these are called here digital numbers or DN values. So basically image is here, you can see finally when you zoom it, you see the arrangement of numbers in the form of rows and columns. So here you see rows and here you see the columns. So image definition is changing when you are doing image processing. So when you are doing image processing, the definition of image will be, it is a rows and column, the numbers which are arranged in the form of rows and column. If you have multispectral image, which has large number of bands, or if it is a hyperspectral image, it has more number of bands. So in that case, the definition, this rows and column with numbers, you will have multiple arrays. Each array is having rows and column and having some values. So if you have 10 band image, that is multispectral 10 band image, you will have 10 arrays. Each array is representing one band. So this is the one we should understand, the mathematical way to define an image. If I draw just a 2-band image, so you will have here initially here two matrix which are holding some numbers. So this is the matrix 1 and this is your matrix 2. Why I'm talking about again is giving more stress to define image in the form of matrix, because all the processing is happening in the form of matrix and in the form of vectors. So here you can see the two band image B1 and B2 is nothing, basically it is matrix 1 and matrix 2. It is two-dimensional matrix and it has numbers here. Now if you overlay these and if I talk about the vector, how to define the vector in this case, if you take first pixel, the first pixel here and the same first pixel will be picked up here because they are just co-registered bands. So here the value, suppose it is 20 and here the value is 100. And if I ask what is the vector value of first one, the first vector will be looking like this. Vector x 20 I plus 100 j. So here I and j is the two components which is coming from your matrix 1 and matrix 2, and the elements are 20 and 100. So 20 is coming from first matrix and 100 is coming from second matrix from same location. So this is the vector and this complete is a matrix. So you can see a similarity between image, matrix and a vector. So next time when I talk about vector, you should understand what I'm talking about. If you have a 10 number of bands or 20 number of bands, the dimensionality of this vector will be accordingly changed. If it is 20 dimensional image, here you will see there are 20 elements of the vector because vector has elements. Here if I talk about x bar, a I plus b j. So here a and b are the vector elements. So you can see we have just seen the image like this or like this. So this is the image where we want to visualize the ground. Maybe the rose, we want to see how the rose looks or how the sweet baby looks, or the satellite image which I've shown you here with sea and the ground portion, how it is looking. This is one method to visualize. Visualize means to see the ground phenomena. Ground phenomena, what are there on the ground, different objects we want to see. So that is called visualization. So visualization means to see the phenomena or to see the ground through image. That is one method when we try to see the ground through image. The image is one form. Same information we can see in the form of vector. So here what has happened, if I take the vector elements and the image is my three-dimensional, 3 bands, physically we can have maximum 3 axes, x, y and z. So maximum here I can take a 3-dimensional image which I can plot. If I take 1 pixel, I will get 3 values because my image is 3-dimensional. I will have the vector will be 3-dimensional vector, and I can display that vector element on 3 axes and I can plot the different objects. Suppose the agriculture may be coming like yellow, forest may be coming like green. This way it is plotted here. The built up buildings are coming like here, like this, and the water is coming here, and some dry land is coming somewhere here. So these are the same objects which are plotted in the feature space. So this is called feature space. I can plot the image or I can see the object not through image like the previous images I've shown you. I am visualizing the ground through feature space, and in the feature space I can plot these vectors. So if my image is 2-dimensional, you can simply plot the vector like this. Or here I can plot again. Here you take here B1 value will come here and B2 value will come here. Now if you have two values like 20 and 100, so here you take the 20 value for the first pixel and here you take the 100 value for on the second band pixel value, and if you join them here, the point will come somewhere here. So this, if you draw the arrow, so this is your vector, feature vector, and you are plotting this vector in this feature space. This is called complete area, is called feature vector, and here you are plotting all the pixels. Now here the pixels will be called feature vector. Each pixel what you take, its dimension will be equal to the number of bands in the image has. Here I have taken the example of 2 band value. So here you can plot any pixel in the form of feature vector. Okay. The limitation is because physically we can have maximum 3 axes, X, Y, and Z. So we can plot maximum 3 bands at a time. In my image, there can be 10 bands, 20 bands, 100 bands, but I can plot only 3 bands at a time. That's the limitation of this feature space. But we can visualize, we can see how the objects are looking through the image and not the image on the feature space, right? So here you can see the agriculture, built up, forest, water, and so forth. Now coming to the first subtopic which I want to cover, it is very, very important to talk about separability analysis. Separability analysis means previously this process was very, very important. Nowadays, it is not so much important when we are working with multispectral image, but still there are specific applications when we are working for temporal data. I will give you some hint of working with temporal images, how this separability analysis is very, very important. Its application is to find out the optimum number of bands to map the objects which I am looking. Suppose there are previously, why this analysis was very, very important, because our PCs or laptops was not so much strong processing capabilities. Their RAM was just in MBs and the image was quite big for them. So it is very difficult to process the images which are very large in the form of rows and column, and they have large number of bands, suppose 8 or 10 bands. So this methodology was developed called separability analysis. So the objective here is if I want to map 4 objects like water body, settlement, forest, and built up. So there are 4 objects: forest, built up, settlement, and agriculture. And there are 10 bands. My processing capability in the PC or laptop is not very large. So what we can do, we can cut down some of the bands. So how to reduce the bands? And reduce means the redundant band, the bands having same information in the image, we can remove them. And out of 10, we can take only 6 bands. So how I should know what are the 6 bands or 7 bands should be considered for classification? So process is called separability analysis. So through separability, I can know that out of 10 bands, I require only 6 bands. I require only 7 bands. Like I can give you the real time example, real life example, like in a cricket. The cricket team, the players, there are 15 players. Nowadays, Asian Cup is going on. Any team in there, you see, they have 15 players. Next month, there is a World Cup tournament is coming up in India for cricket again. So there, they have announced that in each team there should be 15 players, but the final playing are not 15, there are 11. So question is, what are the 11 players you will select out of 15? So 15 is a team of players, but out of 15, you have to select only 11 players. So you have to select the 11 players which are very unique. They are not same. They are not having same characteristics. So you have to take these players very unique. And same way, if you have 10 bands and your processing capability is not very large in your laptop or in your PC, you will try to remove some of the bands which are redundant, which are giving same type of information. You will not consider. So how to do that? The process is through separability analysis. Nowadays, you are getting 8 GB, 16 GB RAM, and very good processor of system is i7 like that in laptop and PC. So you don't feel the processing time is very large. Within 1 minute, you can process the 10 band image. But still, when you are processing the temporal images, the question comes, how many temporal images you have to use for mapping specific class? So how to know that how many temporal images are required? You have to go for separability analysis. So this separability analysis, you have to also understand the input data here is not image. The input data is the training data of each class. If you are mapping 4 classes, for each class, you require the training data. So here, basically the separability analysis means quantitatively we have to select which subset of bands out of 10 bands, how many bands, subset, out of 10, only 6 or only 4 bands are required. These bands or features are required to provide the greatest degree of statistical separability between different classes I'm looking. That means I'm looking water, I'm looking built up, I'm looking agriculture, I'm looking forest. So what are the optimum number of bands out of 10 which should be selected so that which gives the maximum separation between water, built up, agriculture and forest. So that is the objective of separability analysis, and this does the things quantitatively. With some quantitative values we can find out the subset bands. So here it is a discrimination technique that allow separation of the major land cover categories with a minimum of error and a minimum number of bands. So error in the classification will be minimum, and this will use minimum number of bands, not all the bands from the given image. So here, if we have the training data of each class, so this methodology works or requires the training data of each class of water, built up, agriculture and forest. So if we have the training data of each class from each band are normal distributed. So that is one condition also, because we are using some methods of separability analysis. These methods follow the normal distribution. My data should be normally distributed. Then it is possible to use the following models for separability analysis. One is transform divergence. Second is Jeffrey-Matsushita distance. These are the two, and there are two more. You can, when you are, if you are doing in IIRS, creating the signature file for supervised classification. So there you have an option to go for separability analysis, and you get all these methods called transform divergence, Jeffrey-Matsushita distance, and you get two more. One is Euclidean distance, and the second is the graphical method that I can explain in the coming slides. So graphical method means you can plot maximum 3 bands, 3 axes. That means 3 bands you can plot on these 3 axes. Your B1, suppose B1 you are putting here, B2 you are putting here, and B3 you are putting here. So you can plot all the feature vectors here. So this can be water, this can be forest, and this can be built up. If you are extracting 3 class, so here you can see while you are plotting the band 1, band 2, band 3, this gives you clear-cut separation between all 3 classes. So that means these 3 bands are sufficient to distinguish between forest, water, and built up. But if you have more bands, so you have to go on swapping the different bands on the 3 axes and then find out what band combination should be chosen to separate these 3 classes. So here this is a graphical method we are using. Graphically we are plotting our data or image bands, and then selecting what are the optimum number of bands. The second is the distance method. So distance means here you can use the Euclidean distance, d square, which is a difference of vector 1 minus vector j. So this is coming from class 1 and this is coming from class 2. So if you here you can get you can get different combinations in the 3 bands. Distance between built up to water, built up to forest, and forest to water when you're taking 3 bands. So here you can take the combination starting with band 1, band 2, band 3, band 4, band 5, and so forth. If you have 6 bands, you can take maximum from band 1 to band 6. That means if you're taking only one band, so out of 6, only 1 band will be plotted. So your data is just plotted in 1 dimensional. If you're taking 2 bands, then any 2 bands can be considered. So here basically you are calculating the distance between 2 classes. The class can be 1 and 2 or 3. Any of the 2 class you're taking at a time to find out the distance, and that distance should be maximum. So the algorithm can tell what is the best combination out of from 1 to 6. It can be only 1 band, or you're taking 2 bands at a time, or you're taking 3 bands at a time, or you're taking 4 bands at a time. That means 4 bands means out of 6, what are the 4? So you can have different permutation combinations, and you have to find out which combination is giving the maximum separation between all 3 classes. So this is your Euclidean method. And next is here is your graphical. I have already told. In the statistical, you have the transform divergence. So here first, this calculates the one parameter called divergence using the mean and variance covariance. So here this is the mean from the training data, and V is the variance. So this is always calculated between 2 classes. So class can be C and D. Using the training data, you can calculate the mean, and you can calculate the covariance value. And if you put it here, you can get the divergence variable. If you put this divergence value here in this equation, you can get the transformed divergence. So since it is scaled to 2000, so you will get the value from 0 to 2000. So if your value is close to 2000, it's excellent class separation. If it is above 1900, it is good separation. If it is below 1700, it is poor separation. So this transform or separability analysis you can read from Jensen book on digital image processing. That is very good, and they have used the Landsat data. From Landsat, they have explained these methods. Next is the Jeffrey-Matsushita distance. So this is again your statistical method. Here the data should be Gaussian in nature. It removes the least effective bands or features, transform the pixel vector into a new set of coordinates in which the least effective bands are removed. So here again using the mean and variance covariance parameter from the training data of each class. So here class can be C or D or more number of class, but at a time we have to take only 2 class at a time. So you can get the variable called BHAT, and if you put the BHAT value in this equation, you can get the Jeffrey-Matsushita distance. So here also you may get some value, like in the previous case you are getting the values from 0 to 2000. So here also you will get some value. So if the value is higher, that is good, excellent separation. If the value is low, it will be poor separation between class. So we have to take care before going for classification. The separation between classes is very good, so that algorithm can easily separate the classes and do the classification and give us the very good accuracy of our classified map. Now coming to digital image classification. Previously we were doing visual interpretation when we were getting the hard copy satellite images in the year of 90s and up to 2000 around. The people were getting the hard copy printouts. So they were doing visual interpretation. Visually they were identifying this is a forest patch, this is a water body like a lake or a canal or some pond or some river, and this is a built up area, this is your agricultural land with crop, without crop, like that. So they were doing visual interpretation, tracing the features using the tracing paper. Nowadays the visual interpretation is having very good accuracy since it is done by human being directly, so they have very good accuracy. But when we have to process large number of images, it takes a lot of time. So it cannot we cannot process so fast. Each image takes a lot of time, and when we have multiple images, we may require weeks or months to process larger number of images. So it is very time consuming, and again it is coming on the tracing paper, so we cannot use directly in the GIS tool. You will be learning GIS in the coming modules, so that it can handle the large number of layers of different classes. So again, since it is a hard copy, you have to again digitize and take it into a GIS environment. But here, if you are going for digital approach in place of visual approach for classification, so it is very quick, and within short time you can get the results. Of course, the accuracy will be a little lower, but nowadays there are techniques coming up. There are very good satellite images coming up from 30 meter. Today you have 3 meter, 1 meter, or less than 1 meter pixel size satellite images per day basis, and lot of images are free also for research point of view or commercially if you want to use them. So many advancement has been happened while acquiring the remote sensing images. So digital image classification is very important approach to be used. Basic objective of digital image classification is, the question is why we should go for digital image classification. The answer is when we want to prepare land use, land cover or thematic map, where we want to extract the water body, built up area, forested area, agricultural land with crop, without crop, barren land, and so forth. So we can go for digital image classification. So objective of this operation is to replace the visual analysis of the image data with quantitative techniques for automating the identification of the features or objects in a satellite scene. So here you can see one example of remote sensing image, which is of 5 bands here. And as per the definition of the image, each band is coming as in the form of matrix having rows and column, and there is a number. So each number is placed in the form of rows and column, and there are 5 arrays. So whatever classification technique you apply, you get the output like this. It is single layer output, again in the form of matrix having rows and column. This side your column and this side your rows, and each number is represented by rows and column, its location, and each number has some label. Like if you see the blue color or sand color, which is water, and its number should be 1. The vegetation is green color, and that is number with 2 numerically, and wetland is by 3 number, and soil is by 4 number. Because in the image you cannot handle the text, you can only handle the number. So it can be float or digital float or integer number. Generally remote sensing images have the integer numbers, and here just symbolically we are representing by numbers as an output, classified output. 1 is for water, 2 is for vegetation, 3 for wetland, and 4 is for soil. So today I'll be talking about very conventional and very basic classification algorithms, and they're categorized with 3 or 4 words. They are pixel based. Pixel based means whatever algorithm I will talk, they are using the pixel information. That's why they are using just pixel information. For the human being point of view, when we try to recognize the objects, sometimes we give weightage to the color. So with respect to color, we identify the object. So here the pixel can be equally represented as a color to try to recognize the object. So as the human being recognize object with respect to color, one of the parameter we consider, same way here algorithm will be using the pixel value. So that's why these algorithms are pixel based. Second category for this same algorithm is coming as statistical. That means they are using some statistical parameter like mean, mode, variance, covariance, standard deviation, so forth. So these are all your statistical parameters. So these algorithms are also called statistical algorithms because they are using statistical parameters. Then third is parametric. Parametric means they're all the parameters you can calculate. You don't have to optimize with the trial and error. So, and also if you apply the same algorithm on multiple images, the performance of the algorithm will remain same. You don't have to go on tuning the algorithm for different image, the parameter is different. The parameters in the algorithm will remain same. So that way, these algorithms are also called parametric. So these algorithms have 3 names: pixel based because they are using pixel information, that is, and they're statistical. They are using only the statistical parameters like mean, mode, standard deviation, and so forth. Parametric, their parameters are not optimized with trial and error. Algorithm you use on one image or multiple images, its performance will remain same because you don't have to optimize the parameters. So that's why they are parametric classifiers. So, and they also have 2 subcategories in classification. One is unsupervised. So in unsupervised, you have very limited algorithms because the algorithm should be very easy to work. And the algorithm here is C means or K means. Here C is represented as cluster and mean is the parameter in the statistics. It is using from the image, it generates the mean parameter, and mean is like if you have few numbers and you calculate the average value, that is called mean value. And C or K is representing the number of clusters. So this unsupervised classification is also called clustering approach. Clustering approach, and through clustering approach we get the clusters like cluster 1, cluster 2, cluster 3, cluster 4. So what is the difference between cluster and classification? In the clusters, the name is missing. We are just calling them 1, 2, 3, or cluster 1, cluster 2, or class 1, class 2, class 3. The labels are missing. Labels means we do not know cluster 1 is water, or it is settlement, or it is forest. Actual class name is missing, right? Second, if you talk about the supervised classification, here the conventional, there are 4 algorithms. One is minimum distance classification. Second is Mahalanobis classifier. Third is parallelopiped or box classifier. And fourth one is maximum likelihood classifier. And then on Friday, in the next lecture, I will talk about classification accuracy. So if you just talk about unsupervised classification or clustering approach, we take the image, suppose 3-band image or 5-band image, whatever image we have, we take that image and we define, we give to the algorithm number of clusters. We want to divide the image into how many clusters. Suppose clusters can be 3. So here C value will be 3. Plus we also have to define the number of iterations. How many times the algorithm should iterate. Plus, we can add some extra parameter, the mean shift. At every iteration, how much mean shift is there, that is delta. And this delta should be less than or equal to delta naught. So delta naught is defined by the user value. Suppose it is value is 0.9. So my delta should be less than 0.9 or equal to 0.9. So it is an OR condition to stop the iterative process. So algorithm will stop as the number of iterations it has reached, or my delta mean shift error is less than delta naught, which I've defined. It is 0.9. I can define 0.9. I can define 1. I can define 2. It is just by the user a particular threshold. Like in a class, you get 60% passing marks. So passing marks is a cutoff. Below that, the student is fail, and above 60 or equal to 60, it is pass. So these 3 things we have to define before this algorithm has to work. So here also here we have not defined unsupervised. Like if you see in your schools, colleges, nowadays you are studying in colleges and in the university, but still you have classes. So there the class can be 2 types, supervised class and unsupervised class. Supervised class means there is a teacher with you and he's teaching the topic. Unsupervised means teacher comes to class and gives some questions and goes off. Maybe the teacher is busy or not well. In both the cases, he may give you some questions and you have to learn these questions to understand the topic. So in that case, the class is unsupervised. So here the also algorithm does not know anything. The student does not know anything about the questions. What can be the answer of the question? The unsupervised class, the student has to get the answer of the questions by themselves. So when the student learns the question by themselves, they feel quite difficulty to get the actual answer, and they are not confident that whatever answer they have got, is it the correct answer or further improvement in the answer is required. So when there is unsupervised class, the student, what it does, it learns by themselves first the question, and he's not confident. Then he asks to his friend, is it correct? So second iteration he has done. First iteration is learning by themselves. Second iteration is learning through a friend. Third iteration is he or she can go to library and refer some book. Fourth iteration is he can refer internet, and he can go on doing this different mode of learning, so that he built a large confidence that yes, this is the more or less correct answer. Still, he is not so much confident, but he feels this is the more or less correct answer of the question given by the teacher. So here what is happening when the class is unsupervised, the student is learning number of times to understand the topic, initially by herself, then asking to the friend, then referring books, and then referring internet, and so forth. So he is doing learning by large number of iterative process. Same thing you can see in unsupervised classification approach also. Algorithm is learning by themselves. Learning means calculating its own parameters and refining it, because initially the parameter was assumed, and number of times assumptions are not correct. In the night you can see some hanging thing and you feel it is a snake, but morning when you see, oh, it is a rope. So you have assumed in the night that is snake, but actually it was rope. So what I want to say, the assumptions are not always correct. So algorithm has to start and some of the parameters of the algorithm should be known to the algorithm. The value, what is the value of that parameter, and which is unknown because it is unsupervised, nothing extra parameter, nothing extra data is given to the algorithm, only the image is given to classify. So algorithm does not have any extra information. So some of the parameters has to be initialized, but there is no information. So algorithm, what it does, it assumes that parameter, and that assumption cannot be correct. So to achieve more or less correct value of that parameter, algorithm has to do iteration. And when to stop, we can put two conditions. Either it has reached to the maximum iteration value we have given, suppose it is 10, so it will stop, or condition if before 10 it is reaching, the delta value has reached to equal to or less than delta naught, then again it will stop. Okay, so here I can explain. If we have two band image, again we have to understand the image is a matrix and vectors, so that we can understand the processing of this unsupervised classification. So this is your band 1 and this is your band 2. Band 2. Now how this algorithm will work, so we can plot the feature space. This is your B1 and this is your B2. You can plot all these pixels now here. So they are coming like this. All the pixels of the image you have plotted in here. Now the objective is you want to group these pixels into suppose 3 classes. You are taking C is equal to 3. And you have to also define some extra value to the algorithm and number of iterations. Suppose you have taken 10 and delta naught you have defined to be 0.9. This is a mean shift. At every iteration, mean is shifting. So I'll tell you how it is. So this, if you see here, which algorithm it is using C means or K means. So what this algorithm means, here in the C means it is using the Euclidean distance. So here D will be mode of 2 vector difference xi minus x bar I. So here you can, this is your J. So here I is going from 1 to n. This n is different. I can take it maybe small value. So this is your pixels in the image. Each pixel 1 to n here, and j is your number of clusters, that is your 1, 2 and 3. This is your clusters, because we have defined n is equal to 3. So j will be 1, 2 and 3. Why I'm not telling the 1, 2, 3 is a water, forest and agriculture? Because we do not have any ground information from this image or about the study area. We do not have any ground information. We have only the image of that area. So I do not know where is water, where is forest and where is built up. So here the label will be 1, 2, 3, cluster 1, cluster 2, cluster 3. So here in this equation, if you see equilibrium distance, it is I and j for ith pixel and for jth class. So here is your unknown pixel. That is xi. It can be 1, 2, 3, any pixel, unknown pixel. This is your unknown pixel. And this is your mean of the cluster. Mean of cluster. So here, since it is unsupervised, xi I can get from the image, first pixel, second pixel, third pixel, one by one. But how I can get xj bar? So xj bar will be x1, x bar 1 for first class, for first cluster, x bar 2 for second cluster, and x bar 3 for third cluster. These are unknown to me, so it is a question mark because I don't have any ground information. So the mean value of each cluster is unknown to us. So what we can do, we can assume the mean vector of cluster 1, mean vector of cluster 2, and mean vector of cluster 3. Since my image is two-dimensional, my vector assumed here will be again two-dimensional. I can assume value here 0 and 150. I can assume here this value, suppose 120 and 50. Any value I can assume because it is assumption, right? In the night you have assumed it is a snake. Somebody can assume something else, but in the daytime you see it is only rope. So assumption can be something, anything you can assume here. You are free to do that. Suppose it is 240 and 100. So now your mean value is known to you, which was assumed value, no problem, but it is known. You can plot them here. X1 bar, X2 bar, and X3 bar. Now here you can see mean value is known to you and which is plotted in this feature space, and there are unknown feature vector also. So now you can use this distance criteria because when you are doing classification, we are taking some criteria value. So here we have taken the distance as a criteria, which is easy. It has a very simple and one parameter, that is mean, and mean value we can assume and we can refine it. If I take other parameters like standard deviation, variance covariance, they are very complicated parameters which cannot be refined through iterative process. If you can do it, it will take large number of time, number of days are required. So that may be still not possible, not sure we can assume it or not, we can refine it or not. So that's why in unsupervised we have to take the algorithm which are using the simplest statistical parameters. So that is mean has been taken, which is very simple to do that. In a normal classification, when you want to divide, when you have a very big basket of fruit, and if I say separate the fruits of with respect to a similarity, you segregate them: apple in one basket, banana in second basket, pineapple in third basket, guava in fourth basket. So you are using some criteria of color and their taste and their shape, and according to these parameters you are dividing them into separate baskets. So here also we have to take some criteria, and the criteria is the minimum distance criteria. So if this is the first pixel in this feature space, we can find out distance here, D first pixel, first cluster, then D here, first pixel, second cluster. Then D here, first pixel, third cluster. Now find out which is minimum. So it looks D13 is minimum. So this pixel will be labeled to cluster 3. Like this, one by one, you have to label each cluster using this distance criteria, minimum distance criteria. Once all these feature vectors or pixels has been labeled to either 1, 2, or 3 clusters, then what will happen? You will have few pixels in cluster 1, few pixels in cluster 2, few pixels in cluster 3. Now you go back to the original image, and on the original image you can find out which pixels got the label of cluster 1, which pixels got label of cluster 2, and which pixels got label of cluster 3. So whatever pixels were there on the original image having the label 1, use these pixels to get the new mean value of cluster 1. Now you know the pixels which got the, you know the original pixels on the original image which got the cluster label 2. So using these pixels, find out the second mean value x bar 2, and same way you have to find out x bar 3, and previous assumed value should be thrown because this was assumed. Now it is refined, but you can find out here the delta 1 difference between x1 here and x1 here, plus delta 2 you can find out here, and delta 3, that is a mean shift because mean is changing, and that change you can find out with respect to 1, 2, and 3. So you have delta 1, delta 2, and delta 3, and if from here you can find out the mean value, and you check the mean value is less than or equal to delta naught. If this condition is false and your number of iteration is also false, there's only one iteration has been done. So using these new mean values, again do a clustering of all the pixels. So it is second iteration, like the unsupervised class, the students are iterating, initially learning by themselves, then asking to the friend, and again learning, reading the book, again learning, and seeing the internet. So every step is an iteration. So here second iteration is coming. Again, we have the new mean values. Using the new mean values and using this distance criteria, again label all the pixels to either cluster 1, to either cluster 2, or cluster 3. Once you have few pixels in cluster 1, in cluster 2, and cluster 3, whatever pixels you got in cluster 1, find out new mean value here, new mean value here, and new mean value here. So you got the one more new mean value. So these previous values will be thrown off, but parallelly you get again delta 1, delta 2, and delta 3, and again find out delta mean and compare with delta naught. If this condition is false, still your mean delta mean is larger than delta naught, and here you have second iteration, it is still condition is valid for both the case. So you have to go for third iteration. So like this you can go on doing iteration till you reach to the maximum number of iteration, that is 10, or your delta m is less than 0.9, which we have defined. So if any of the condition is true, algorithm will stop, and then what will happen? You will get a few pixels for here, few pixels for, let me just take some other color. You will get here a few pixels for water, a few pixels for forest. Sorry, that is not water. It is cluster 1, and second for cluster 2, and third is for cluster 3. So here output will be like this. So these pixels belongs to cluster 1, these pixel belongs to cluster 2, and this pixel belongs to cluster 3, suppose. But I do not know what is cluster 1 on the ground. It is water, forest, that we have to cross check, go to the ground and find out its label. Since it is unsupervised, we do not provide any training data, so label will be also missing. So this is the way unsupervised classification works. The question comes, what is the application of unsupervised classification? When you have an image of an area, when you have an image of an area and you have not gone to the ground, but you see different shades. So application of unsupervised means you can run the unsupervised algorithm. And initially what you can do, since you have not gone to the ground, you do not know how many classes are present, what type of classes are present. You can give my C is 50. So you divide the image into 50 clusters. And later on, using some reference information, or go to the ground and try to merge some of the clusters which are same, because you may get multiple clusters. Suppose this cluster and this cluster, both are water. So both will be merged because the label will be same later on. The label was maybe initially 1 and 2, but now you can change the label to be water. So both are merged. So what will happen? You may get finally, in place of 50, you got only 30 classes. So application of unsupervised classification is you can know without going to ground how many maximum classes you can map, you can extract from this given image for the given area. So that is only application of unsupervised classification. So now we'll go for supervised classification. As I listed previously, I will cover here only 2 supervised classification, and tomorrow or day after tomorrow in the next lecture, I will cover rest supervised classification because time is running. So supervised classification, the difference between supervised and unsupervised means we are providing here training data. So again, here you can see we have 3-band image, but from this image, we have taken a few samples for water, few samples for agriculture, and few samples for barren land or rock. And we have the labels also. We know the A is representing to water, B is representing to agriculture, and C is representing to rock. So when we apply the training data on the image, and again C mean algorithm, that the first one we apply, the output will be like this, where we can see again 3 segments, and we can know the label of the segments. This is your water, this is your agriculture, and this is your rock. In the previous case, the label was missing because there was no training data, right? So here in the supervised classification, we can have the conventional 4 algorithms. One is minimum distance classification. Second is Mahalanobis distance. Third is parallelopiped. Fourth is maximum likelihood classifier. So let's start the first one, minimum distance classification. So here, this is same like which I've explained in the case of unsupervised algorithm. So again, you have band 1. And band 2. B2. Since it is supervised, that means we are again extracting some of the known classes, like for water. So for first class is water. So once we know this is water, that means we have gone to the ground for the same area, and a few water bodies we can locate. Where is the water body? Suppose this is the water body here. On both the bands we can see. So this is your water body, and this is a river here. So on this river and on the water body, we can take few pixels. Suppose 1, second, and so forth. Suppose 10 pixels we can take, and its value on xi and x2. On band 1, we are getting few values. Suppose 10, 20, here 11, 25. Like this, the value is coming here 9 and 22. So here we are getting pixel values. So we can calculate the mean. Mean for water we can calculate here and here. Same way, if I take forest, so again I will have the vector samples 1, 2, 3, and so forth. Suppose 12 samples I have taken. So here value can be 50 and 150, like that. we can calculate the mean for forest. The third sample is your agriculture class. Again, you can take first sample, second sample, third sample, and so forth. Suppose 15 samples you have taken, and this is your mean. You can calculate X bar AG for agriculture. So this value can be 75 and 200. Just for example, I'm just taking randomly values to give you feel. And here you can calculate the mean once you have all the samples. So again, if you take here feature space, how this algorithm will work. This is your B1 and this is your B2 axis. And you can plot all the pixels of the image here. Since it is supervised, so you know the label mean vector for water is coming somewhere here. And mean vector for agriculture is coming somewhere here. Sorry, agriculture is coming here, and for forest it is coming somewhere here. And the equation is, the distance equation is D is equal to Dij here mod, it is mod of Xi minus Xj bar. So rest parameter, you know, this is a known pixel, this is a mean vector of class. So here you have three classes. So how the algorithm will work, if you take first pixel, you have to find out here D1W, and here you have to find out B1 forest, and here you have to find out D1 means first pixel with agriculture. And now you compare which is minimum. Suppose for forest it is minimum. The first pixel got the label of, if I draw the output image in the form of matrix. So this label will come as forest. So in single iteration, since it is supervised, we have a training data. So using the training data of each class, that is samples of each class, we can calculate the mean parameter, because we are using here minimum distance algorithm here, minimum distance, which is using the C means algorithm. So here the algorithm used is C means. So C mean algorithm is using the Euclidean distance, which is like under root x1 minus y1 ka square plus x2 minus y2 ka square, like that. So this is shortest form mod of it is given. So this is unknown pixel, and this is a mean pixel. Mean feature vector we can calculate from each class. So for each class you can calculate D1W, D1F, and D1 agriculture. If you take second pixel, this will become D2W, D2 forest, and D2 agriculture. For third feature vector, this will be D3W, D3 forest, and D3 agriculture, like that. And then compare for which it is minimum, the distance is minimum. So like this you can do in single iteration. You will get all the labels of these pixels in this, and you can get the output. Since it is supervised, we don't have to do iteration. So same way in a class when the teacher is teaching, so whatever teacher speaks, whatever teacher writes on the board, you take it 100% correct. You don't have to ask to your friends, you don't have to refer the book, or you don't have to read the internet. Whatever she has taught, you take it 100%, it's correct. In single iteration, you understand the topic. When it is unsupervised, you have to do number of iterations to understand the topic. So same way here, when it is supervised, when we have the training data of each class, we can calculate the parameters required for the algorithm. Since we are using here Euclidean distance, it requires only mean parameter of each class. So we can calculate the mean parameter of each class from this given training data. Now, second algorithm here, you see Mahalanobis distance. So there is very small difference. In Mahalanobis distance, the distance will be not what I have written here, this one. It will be different. This will be coming like, if I take D square I and J, so it will be coming like Xi minus Xj bar transpose. As I told you, image is a matrix and array. So here you can see the example of arrays, vector A inverse, then xi minus x bar j. So here this is a difference of vectors. Since my image is suppose image is having n bands, so this is your bands in the image. So this vector difference, which is in the form of matrix, this will be 1 into n. This is n into n, and this will be n into 1. Why? Then only you can multiply. These should be same. Then only you can multiply the two matrix. So here these are two matrix you can multiply, and here this is this common. Then again you can multiply. Finally, it will be 1 into 1. Single value will come. The distance will come as single value. Now here if you see, this is your unknown pixel. Pixel. This is your mean, as I told you previously. This is your transpose, operation in the matrix. And this is A inverse is a weight matrix. Weight matrix here, it has three norms. Unit matrix, it will be variance covariance matrix, or it can be diagonal variance covariance matrix. So when you take A inverse as a unit matrix, unit matrix example, if it is here, your two band image, your unit matrix will be like this: 1, 0, 0, 1. The unit matrix has diagonal elements are unit value, and other elements are 0. Then it's called identity matrix or unit matrix. So when you take A inverse as a unit matrix, your classification becomes Euclidean distance, or C means classifier. The distance becomes Euclidean distance, right? But when you take A inverse as a variance covariance matrix, you can calculate the variance covariance from the given training data. I can tell you later the formula for it to get the variance covariance, right? Then it becomes your Mahalanobis distance, Mahalanobis classifier. That means your distance is modified. Your distance is coming like this of transpose with variance covariance with this one, right? And third is again a modified version of Mahalanobis, that is diagonal variance covariance. So if you have here variance covariance matrix and you take only the diagonal elements and other elements are 0, then this becomes your diagonal variance covariance. Sorry, you get the diagonal variance covariance matrix. So these elements are retained and other elements are 0 in the variance covariance matrix. Then this becomes diagonal variance covariance matrix. If you just explore in the internet, Mahalanobis is a Bengali name. He was a professor in Indian Statistical Institute, Calcutta, and he has proposed this distance. And on his name itself, this distance has came up, Mahalanobis distance, where algorithm is using the variance covariance matrix. The formula for variance covariance matrix, I'll just take the blank slide where I can write somewhere here. Let me write here. It will be a little clumsy. Here I can write the variance covariance element. If you see the element, element will be, suppose I and J in the matrix, it is the element. So how to calculate? It is your n into n minus 1. It is xi summation. It is summation of xi minus xj and yi minus yj. So these are your mean. These are mean element. So if you see here in the training data, you have the elements here on the each band and the mean value. elements, 10 elements, and its mean value. So here in this equation, this is the element and this is the mean. This is the element and this is the mean. So you have to go on doing it for all the elements. You can calculate. If you know the matrix is coming like this, if it is 2-dimensional, the elements will be like R1, or I can type here C, so that you don't get confused. You type here, this is your C11, C12, C21, and C22. So here you take only one element. Here this is 1 and this is 1. What do you mean by 1? 1 means this is again 1, and same 1 will be coming in the second point also. This will remain 1. This is 1, 2. That means 1 is this one and 2 is this one. And here this is reverse of it. This is negative. This 2, 1. So again this is 2 and this is 1, and here this is 2, 2. And n is number of samples here. So here n is number of samples. So like this, you can calculate all these elements. I and j is the elements here of variance covariance. This is a variance covariance matrix. So these things you may not get the book, but in some of the papers you can find out. So overall, I'm stopping here. And before that, I can just in today's lecture as an image classification techniques, I talked about to understand what is an image, mathematical form, like in the form matrix and the vector. Then I talked about the separability analysis, the graphical method, Euclidean method, the transform divergence method, and the Jeffrey-Matthews distance method, where you can subset and find out the least redundant bands, and you can use them so that your processing time is minimized. Then I talked about definition of digital image classification, comparing it with the visual classification. And then I talked about supervised and unsupervised methods. And also I mentioned you the algorithms which I'm talking about. They are pixel based, statistical and parametric algorithms. And I talked about the unsupervised, that is C-means or K-mean algorithm, how it works mathematically. And the two algorithms of supervised also I explained, that is your Euclidean or minimum distance classifier, which is using Euclidean distance, and second is Mahalanobis classifier using the Mahalanobis distance mathematically. So today I'm stopping. In the next lecture, the second lecture also on Friday. At the same time, I will be covering the two left out supervised classification algorithm, that is parallelopiped or box classifier plus maximum likelihood classifier, and the your accuracy assessment of the classified map. For classification, this was published with CRC Press. It is online available, and the hard copy also you can refer in your libraries. If it is not there, it is a very good book if you want to proceed further for understanding the fuzzy-based classification algorithms. And we got the second book also on the same line, 2020, which I will be talking about in my next lecture. So any questions on my today's lecture? Most welcome. Otherwise, I'm stopping here. Thank you all for listening to this lecture.